Electromechanical instruments. Permanent magnet moving coil instruments. Deflection instrument fundamentals. Deflecting force causes the pointer to move from its zero position when a current flows. Is magnetic force, the current sets up a magnetic field that interacts with the field of the permanent magnet, see figure 3.1a. Controlling force is provided by spiral springs, figure 3.1b. Retain the coil and pointer at their zero position when no current is flowing. When current flows, the springs wind up as the coil rotates, and the force they exert on the coil increases. The coil and pointer stop rotating when the controlling force becomes equal to the deflecting force. The spring material must be non-magnetic to avoid any magnetic field influence on the controlling force. Since the springs are used to make electrical connection to the coil, they must have a low resistance. Damping force is required to minimize, or damp out, the oscillations. Must be present only when the coil is in motion, thus it must be generated by the rotation of the coil. In PMMC instruments, the damping force is normally provided by eddy currents. Eddy currents induced in the coil former set up a magnetic flux that opposes the coil motion, thus damping the oscillations of the coil, see figure 3.2b. Two methods of supporting the moving system of a deflection instrument. Jeweled bearing suspension. Cone-shaped cuts in jeweled ends of pivots. Least possible friction. Shock of an instrument spring supported to absorb such shocks. Taut band method. Much tougher than jeweled bearing. Two flat metal ribbons, phosphor bronze or platinum alloy, are held under tension by spring to support the coil. Because of the spring, the metal ribbons behave like rubber under tension. The ribbons also exert a controlling force as they twist, and they can be used as electrical connections to the moving coil. Much more sensitive than the jeweled bearing type because there is less friction. Extremely rugged, not easily be shattered. Torque equation and scale. When a current I flows through a one-turn coil situated in a magnetic field, a force F is exerted on each side of the coil. Since the force acts on each side of the coil, the total force for a coil of n turns is. The force on each side acts at a radius r, producing a deflecting torque. The controlling torque exerted by the spiral springs is directly proportional to the deformation or wind-up of the springs. Thus, the controlling torque is proportional to the actual angle of deflection of the pointer. For a given deflection, the controlling and deflecting torque are equal. Example 3.1 A PMMC instrument with a 100-turn coil has a magnetic flux density in its air gaps of B equals 0.2 T. The coil dimension RD equals 1 cm and L equals 1.5 cm. Calculate the torque on the coil for a current of 1 mA. Solution.